So the next step is to look in a little bit more detail at the cache. I think this will probably be the last topic for today, and then we'll have lab number 4 will either be for homework or we'll do it tomorrow. But let's just continue on to look at the cache. I've already mentioned that there was a way to measure on an instantaneous manner how many recursive contexts were in use. The word I was looking for before was a gauge. I see I used it in the lab guide, but the recursive context in use is a gauge. It's a number of currently active things. So it can go up and down, like a gas gauge can go up or down. But actually, that's not a good one because it goes up only when you go to the gas station. Maybe a gauge is better, like the speedometer is a better one. But anyway, it shows you the instantaneous rate on the speedometer in your car. But if you want to see which names the server is working on when you have some non-zero recursions happening, that can be useful because it will tell you what the DNS traffic looks like. And so from that, you might be able to recognize that this is an attack or that there's a lot of traffic that's for a specific domain that looks like it's otherwise quite normal, but everything for Facebook or Instagram or something that is all failing. So at least that can give you a hint about where the problem is, and then you can start to look around and check other aspects of the network and other things so that you can find out what's happening. So it's good to know the actual identities of the DNS requests that are being hung up in this recursion that we talked about. And yes, there could be 25,000 entries. If it's completely saturated, this is going to be a huge list. So it's may not be easy to analyze, but it can give you some hints. Even just looking at a few of them will give you some hints about what the issues might be. The other thing that we've briefly seen is the resolver inspect command, which is fabulous for seeing something, seeing what's in the cache. If you look for a domain name that is not in the cache, you will get an error. Of course, it's not really an error in the sense that there was not, that something went wrong. It's just that you asked for something that did not exist in the cache. So maybe it exists in the internet somewhere, but that fully qualified domain name, that specific domain name does not exist. You can see that the yahoo.com might exist, whereas a.yahoo.com, there might be an entry for that. It doesn't exist either, but there is a non-existent proof. Again, here it shows you the SOA non-existence. You can see this last number, the last interval in the SOA, after the serial number and all the secondary synchronization information. 600 represents the negative caching interval. So you can see that the TTL is down to 595. So this indicates that just 5 seconds ago, this entry was created in the cache, and it was created by a query. There must have been a query to CacheServe for a.yahoo.com. CacheServe went out, found out it doesn't exist. How did it know it doesn't exist? Because it got that information from the name server for yahoo.com, from the zone for yahoo.com, and it's going to cache that. It's going to remember that information for another 595 seconds. So this is just to demonstrate that, number one, when I say domain equals yahoo.com, that doesn't necessarily mean that there's nothing underneath yahoo.com in the cache. It means that that specific name isn't found. This also illustrates the idea of negative caching. So things that don't exist also take up space in the cache, which is why some of these random subdomain names results or attacks are so impactful, because negative caching consumes space too. So here's another. We're looking for another. This is an example where we have multiple types that exist at a particular name. So you can see SPF or text records and all that kind of stuff. Now, having looked in the cache, I have to tell you that there is actually a little bit more to the cache than what we just saw. So when I said that there must have been a request for a.yahoo.com, that's why there's a negative cache entry in here. You may be curious about the fact that, well, wait a minute, yahoo.com, we must have talked to yahoo.com at some point, and yes, the name server maybe isn't named yahoo.com, but you'd think that there might be some trace of the information that's needed to talk to yahoo.com should be somewhere. And it is. It turns out that CacheServe uses what's called glue segregation to separate the content that originates from client queries. So all of those requests that arrive at CacheServe, those data are stored in the name cache, and other information such as the name server data, so all the yahoo.com servers information for their name servers, so not their website, but the name servers for yahoo.com, that data is stored, but it's stored in a separate place. It's all part of the overall cache, but there are in effect two caches, a name cache and a delegation cache. So queries, when you use dig and send a request in, the cache that is examined is the name cache. So answers only come out of the name cache. Now, internally, CacheServe uses this delegation information to talk to the name servers and in order to look at these two things, there are separate commands, and a command they use to look in the delegation cache is called inspect delegation. So it's a different animal. It's a different type of data. In some ways, it's less trustworthy, this delegation data. Obviously, CacheServe has to use it. Any name server has to use this information in order to make progress in a resolution. It has to be able to get a referral from one authoritative server and then use that to talk to a second authoritative server. So it's information that is essential for the operation of the DNS. However, it is, in some sense, it is provided by a server that is not the owner. It's not the zone of the target data that it comes from. It comes from a parent of that zone, and so forth. In that sense, it can be. It's easier to exploit, and it can have significant impacts if it is exploited, because it's one thing to spoof, that is to put a bogus entry in the name cache where just users who look for that name are impacted. But if you can effectively spoof something in the delegation cache, then you've managed to hijack a whole domain, like all of .com or all of .br or something like that. I mean, it's so the delegation cache is where data that's needed for lookups is stored. So how do you use this? Again, it's a resolver command, so we inspect delegation. In this example, there's probably been no request for google.com, and so when I look in the delegation cache, I don't see it. In a real production environment, there will be likely some google.com traffic, and so if you send a request there for something in google.com, then you will see in the delegation cache, you will see that google.com has a bunch of name servers. I think there are 4. Last time I looked, they were labeled NS1 through NS4, and you can see the information about the server's name, about where this information came from. So this is from the referral. So this is actually called the glue. The glue was sent from this server that gave us the addresses for the server called NS1. So this is the sense in which the data isn't, in some ways, it's less reliable. It's just not authoritative data. It's from an authoritative server, but it's not from the owner. It's from the parent. So .com, the .com servers, the root, not the root servers, but the top-level domain name servers are the ones that provided this information. If you look up to see what is this IP address, you'll see it's one of the name servers for .com, or at least it was when this slide was prepared. The other thing that you see here, so here you got the address. This is the address of the ns1.google.com, and you got this other piece of data here, which is the round trip time. So what CacheServe will do is it will start to accumulate measurements, how long it takes to talk to all of these servers. And so what the result of that will be that you will find, you will be able to prefer the fastest responding servers. And more importantly, you'll be able to avoid the slow responding servers, but nonetheless, you check those once in a while with what are called probe queries to find out if maybe they've gotten faster, because the one thing that is a constant in the internet is change, I guess like everything in life. So something that was slow or maybe down for maintenance may become the fastest one later on. So that needs to be checked, and there's an algorithm which I can describe if anybody cares about how that's done. But you can see that in the, for example, about authoritative query store, you can see those probes that go out to just measure the time every once in a while. If you see something in the cache that you don't want to be there anymore, so maybe that negative caching that you saw for a.yahoo.com, you want to get rid of that because you know now Yahoo actually has a.yahoo.com, and the customer is complaining, oh, well, it tells me that it doesn't exist, but it really does. You can flush something. So you can flush either an individual name, like google.com, that's just the single name. Of course, it'll take all types with it, A, quad A, text, all records. You can do domain, which is like star.akamai.com, so that gets rid of everything. If you flush or delete the domain called dot, there's a tiny little dot there, it's hard to see probably, that means to flush the entire cache. Of course, if you just say resolver.flush and don't specify a target, then it just removes the whole cache and starts over. If you stop CacheServe and restart it, of course, that does the same thing. You start with a fresh cache each time. This next little topic, server.query. Server.query is a really useful tool, particularly when you start talking about some of the SIA, where there's multiple policies in place. This allows us to emulate any client. We don't have to rely on using dig to see what would CacheServe send to a client who asks this DNS for this DNS name and type. And you can even emulate the time of day, and it gives you a lot of great information, like which resolver and view handled this query, what view selector is responsible for sending that. So server.query is an emulator for traffic, but it gives you a lot more information and is a lot more useful. If you compare what you see with server.query versus what you would get with dig, you can see you get all of the same information, plus you get more information because you get CacheServe specific details about the resolver and the view selector and the view. If any policies were run, you also get to see things like you can emulate an arbitrary IP address, which is very difficult to do with dig without like changing the network or doing something like that. So you can emulate a different clients very easily. So server.query is a great tool to play with. Some of the options I already talked about, and you can even pretend as if it was TCP and different flags. So this is DNS stuff. You can specify which resolver to use. You can force resolution. So that means ignore the cached value and go out and do it again. Tracing. Tracing is very cool for learning what CacheServe is doing. And we'll have some examples tomorrow when we come in. I'll do an example of how we can use the trace information, which is basically a step-by-step picture of exactly what CacheServe does when it makes a resolution through an authoritative server. This picture is just another way to think about what the delegation cache is. Remember the yellow boxes here, and we'll stop pretty soon. I know it's 4 o'clock. The delegation from the root servers, when we initially asked for www.ripe.net, the root server said, I don't know who ripe.net is. I mean, what www.ripe.net is. However, I do know that there's a bunch of net servers, and in this glue, the glue in here will be information that says f.gtld-servers.net, and then it gives the IP address. So that information in this red bubble up here is coming from the root server. But in order, the root server is not the authoritative source. It is not the owner of things inside .NET. Things inside .NET, the answers have to come from the .NET server. The root really has no business handing out this information about this name and this IP address. It has to, in order for DNS delegation to work, it has to do it. But it's really not the owner of the data. And so if I want to see what the IP address of f.gtld-servers.net is, what CacheServe would do is CacheServe would ask this server. It would not ask the root server. And so that's the difference between this entry appearing in the name cache versus the same information occurring in the delegation cache. And yes, most of the time, it's probably the same. But there's misconfiguration, and there's deliberate attacks, and so it's kept separate. And this is what I meant when I said that CacheServe was very conservative about how it dealt with results that it learned, and it could have taken this information from the glue and put it into the cache so that a client that happened to ask for that exact name could get the delegation information instead. But a more conservative, a more secure approach is to just keep that data completely separate. And if a client really wants to know this information, then go ask the proper server. Don't rely on its value that you received from the glue. So that's a long answer to what's the difference between the delegation cache and the name cache. And one last remark I'll make about that. Another way to think about the delegation cache, where did the delegation cache go? Here it is that you know how we have preloads, permanent cache entries in the delegation cache? Well, the name cache has these preloads. When we talk about stub zones or stub statements, as they're called in CacheServe, that's like a permanent entry in the delegation cache. So maybe you understood that remark, maybe you didn't. But when we go back and tomorrow, when we talk about a stub is part of a resolution, resolver's configuration, I'll mention this again, that a stub is just it's like a preload, a permanent entry in the delegation cache. So it doesn't get overwritten by the actual glue, but rather it's considered to be a administratively set permanent entry. Okay, so we're out of time for today. What we're going to do is we'll stop here. Tomorrow, if you'd like to get started on exercise 4, that would be great. We'll spend a little bit of time in the morning on this. And I'll also talk about how to use a script to look at the delegation cache and learn some useful information. So we'll just stop here. I'm going to stop the recording.